Section 5 involves working with sets, and we've kind of hit almost all of the topics in this section already. So there's just a little bit of vocab, and we kind of already know what we're doing here, so hopefully this section won't be too tough for you. We've already talked about sets and subsets in this class. Recall that a set is what? What is a set? Yeah, it's like a group of stuff, okay? Like a collection of things, like a baseball card set, a collection of baseball cards. So a set is just a collection of things, but in algebra it would be a collection of numbers. And I'm going to put in parentheses the special word that we have for parts of a set is an element. The parts of a set are called elements. We have a couple ways of representing sets. We have roster form. Roster form is very easy to do. Just list all elements in a set inside squiggly brackets separated by commas. That's roster form. Piece of cake. It does take a while if there's lots of elements. That's for sure. Okay, now set builder notation we've been using. We know that it looks like squiggly bracket and then like x such that maybe x is greater than 2 or something like that. We've seen set builder notation before, but we've only written set builder notation using that sort of look to it. But we can write set builder notation another way, or we can use set builder notation to represent our sets in another way. For example, if I have the roster form of a set that looks like this, 0, 2, 4, 6, and then I put dot, dot, dot. What does that dot, dot, dot mean? So it keeps going, following this pattern. What is the pattern that we see? These are even numbers. But not just even numbers, they are the positive even numbers, right? Because I'm not going dot, dot, dot this way, okay? So in set builder notation, the way that I can write that, because as we pointed out, there's a lot of elements here in this set. It just keeps going. So are you going to sit there and write 0, 2, 4, 6, 8, 10, 12, 14, 16, and just keep going for forever? No, you would never finish, and then that's not how you want to spend your life, right? So instead of doing that, we use set builder notation, squiggly bracket, and then we're going to say, we're just going to pick a letter, so x such that x is a positive even number, and then close the squiggly bracket. So the set builder notation can be used in that way to write down what a set is without having to write down every single element in the set like roster form makes you do. Okay, so how do we use roster form and set builder notation? Well, I just gave you the answer to that question on the previous page. Let's write T is the set of natural numbers that are less than 6 in roster form and in set builder notation. So the first thing we have to do is remember, what are natural numbers? The natural numbers a long time ago, it seems like probably 2 years ago, but actually it was only about a month and a half ago. They are positive whole numbers except for 0. They're the counting numbers. Remember, a long, long time ago, some guy came up with the first number. It was number 1. 1, 2, 3, 4, 5, 6. Those are the natural numbers, all right? But we want the natural numbers that are less than 6. I don't know why there's a quotation mark there. Get rid of that. The natural numbers that are less than 6, and we want to write that in roster form. So roster form of this would be T equals, squiggly bracket, the natural numbers that are less than 6. 1, 2, 3, 4. What about 5? What about 6? Why not 6? Yeah, because it says less than. It doesn't say less than or equal to. So that is the set right there. Form, roster form. Roster form. Looks like farm, I know, but it's roster form. So we want to write that in set builder notation as well. So set builder. Yep, we're going to have squiggly brackets. It's going to be t equals. So again, we write t equals squiggly bracket. And now in set builder notation, we write x such that well, yeah, x is a natural number, so we're going to write x is a natural number. And then we have to put that other condition on there, which says that x is less than 6. Normally that'd all be one line. I just didn't have room to write it all as one line. X is a natural number, and x is less than 6. So that's how we have to write that. For the next one, n is the set of even natural numbers that are less than or equal to 12. We want to write that in set builder and roster form. So it says roster form first. Let's do roster form first. I'll make it look like form this time for you. It says n is the set of. So I'm going to write what? N equals, squiggly bracket, and now even natural numbers. Yeah, the natural numbers are 1, 2, 3, 4, 5, but we just want the evens. So that's 2, 4, 8, 10, and are we including 12 this time? Yeah, because it says less than or equal to, so comma 12. There's your roster form. All the elements are there, written out. Set builder notation. We're going to write n equals again. Squiggly bracket. And now just pick a letter. You could go with x. You could go with little n if you wanted to. We could go with x. Such that x is an even natural number, comma, what? X is less than or equal to 12, and I'll just squeeze that in right there. There you go. That's set builder notation for that guy. Hopefully these 4 problems are going to be very easy for you, considering we've been doing set builder notation in this entire chapter. Normally, if I didn't introduce it to you in the first section, this is where it would be introduced. But you already know how to do it, and you already know how to solve these. So let's just go ahead and do these 4 problems, and then I'll give you some time. So subtract 7 from both sides. And we get negative 5x less than or equal to 10. So now we're going to divide both sides by negative 5. Good. Don't forget to flip the symbol. We divided by a negative, which means we must flip the inequality, and you get negative 2 there. Now we want to write that in set builder notation. The directions say solve and write in set builder notation. We've been doing that for forever. So I just put my such that bar, x, squiggly bracket, and I'm done. This one doesn't specifically say graph, but almost every problem on the quizzes and tests do. So let's go ahead and graph it as well. Here's the negative 2. I'll put maybe a negative 5 here and a positive 1 there. Doesn't say to, but we might as well. Close dot to the right. There you go. Okay, the second one, what do? Subtract 9 from both sides. That's a positive 9. To get it to turn into 0, we subtract 9 from both sides. What do we get? 21 minus 9. 12. And now what? Divide both sides by negative 4. And we get Flip the inequality again because we divided by a negative, and we do get negative 3. So it's n is less than negative 3. That's ready to be put in set builder notation. Such that, put an n out front, squiggly brackets around it, and then let's graph it just because we can. Negative 3 in the middle, negative 4 over here, negative 2 over here. Open and to the left. We're Beyonce today. Third one, what do we do? Subtract 3 from both sides. And we get? Okay. Now what? Divide both sides by negative 4. And we get x is greater than negative 3. That's ready for set builder notation, so there you go. We draw a graph. Negative 3 here, negative 4 there, negative 2 there. Open dot, going to the right, greater than. And the last one, what do we do? Subtract 7. 4y is greater than or equal to 16. Divide both sides by 4, and we get greater than or equal to 4. We did not flip the symbol that time because we did not divide by a negative. So that is ready for set builder notation. If the y was on the other side, we'd have to read that problem backwards, rewrite it forwards, so that then we could put it in set builder notation. Number line, we have 4, 3 and 5, close dot, to the right. Greater than is to the right. I know you want to be Beyonce, but just not the case today. It's all right. 9 through 18 all, you're capable of doing all of that, go for it. I'll give you some time. The next part of this section deals with some notation about sets. So the first thing we're going to talk about is what we call the empty set, which is one of your vocab words. Empty set is a set, but there's nothing in it. So if you think of like a basket, like a picnic basket or something, what would be in that picnic basket if that was your set? Nothing. There'd be nothing in it if it's an empty set. Not even air. There's absolutely nothing there. It's a total void of anything. There are no elements in the empty set. We represent the empty set by writing the circle with a slash through it and squiggles around it. So the squiggles represent set. This symbol right here represents empty. There is nothing there. It's not 0. 0 is something. Okay? This is nothing. Do you understand the difference there? 0 is a number, okay? And there aren't even any numbers in this set. There's nothing there. That's why we can't just write 0. It is the empty set with a slash through the 0. Now, that being said, the empty set is always a subset of any set. Even if your set that you're looking at was the empty set would be a subset of the empty set. Okay? The empty set is always a subset. Remember the day in class when we had everybody stand up and certain people kept sitting down, all the boys sat down, and then, or no, all the girls sat down or whatever it was, and then everybody with blue eyes sat down and so on. And eventually we wound up with no people standing, right? That was the empty set when everybody had already taken a seat. Each one of those that we came up with, each time I said, okay, if you're wearing blue jeans, sit down. The people who were remaining, that was a subset. So what are all of the subsets of the following sets? Here is the set 3, 4, 5. The original set is a subset. Everybody in this classroom is the set, but we can also say everybody who is originally from a different planet take a seat. And nobody would sit down. Everybody who's still standing is a subset. It just so happens that everybody is still standing. Okay, so that's still a subset. So 3, 4, 5 is a subset. Then each element on its own is a subset. So 3 is a subset, 4 is a subset, 5 is a subset. Basically, every possible combination of elements is going to be a subset. So 3, 4 is a subset. 3, 5 is a subset. 4, 5 is a subset. 5, 4 is the same as 4, 5. So you don't have to rearrange the numbers. You just have to have unique numbers in a subset. So notice that we have each individual one. We have just 2, just 2, just 2. Every way that you can have just 2. We have all of the originals. And we also need to include nothing at all, the empty set. Those are all the subsets of 3, 4, 5. For A comma B, this time it's a little bit easier. We only have 2 elements this time. The first subset would be what? AB, the original. Give me another subset. Just A? Also just B. My squiggly brackets are getting much better now because I'm writing them so much. The empty set is also a subset. Is there anything else? We have the original set. We have all of the individuals. B comma A is the same as A comma B, so that doesn't work. The empty set, that's it. Okay? All right, go ahead and try the third one, A comma B comma C. Doesn't matter if it's numbers or letters or shapes or bathroom supplies. It's all the same. What's a subset? A, okay. If I have A, then B is also a subset, and C is also a subset. A, B, and C can be a subset. I heard A, B, A, C. BA is already taken care of by AB. Again, just rearranging the letters doesn't do anything. BC, and also the empty set. And what? Okay. What if I had a D on here as well? So now it's A, B, C, and D. Well, first of all, I'd have to add on this D right here, right? Yeah, I'd have to have not just A, B, C, but also A, B, D. And then A, C, D. And there's a whole bunch more that I have to include. There's a lot of different ways this can all be written here with just 3. I need AD, BD, and CD. I need ABCD. And there's more here. We have ABC, ABD, then ACD, then BCD. So when you have 4 elements, there's a lot. And on the homework, there's a couple. There's one that's like all of the operations: addition, subtraction, multiplication, and division. And it's going to work out to look like this. There's a lot of subsets. Okay? So it's kind of, I think it's kind of fun. Kind of challenging probably to come up with all of them, but make sure you try to get all of them. All right. Think about this one. Let A be this set, x values such that x is less than negative 3. And then let B be this set, x values such that x is less than or equal to 0. The question is A a subset of B? In other words, is everything that's in A also in B? What do you think? No? So to figure this one out, the best way to do it, I think, is to write it out in roster form, just to take a look at what the numbers are going to look like. So for this guy in roster form, I'm going to write A equals x values less than negative 3. So that's like negative 4, negative 5, remember on the negative side, negative 6, and so on, right? And everything in between, like it could be negative 4.2, negative 5.1, things like that. For B, I'm going to write down the same stuff. B equals roster form, x values that are less than or equal to 0. So that would be like 0, and then less than is negative 1, negative 2, negative 3, negative 4, and so on. So is A a subset of B?
Yes.
Yes, it is. Okay? Because B has 0, negative 1, negative 2, and then all of those, just like this one has just these. It starts at negative 4 and goes negative. This one starts earlier than that, but goes negative, includes negative 4, and everything else that set A had. So therefore, the answer is yes. So basically what I just said verbally, this is starting to say on paper y, but B has all of these guys on, all of these guys on. That would be another way you could show it. Okay? Just show me. All right, we have two more vocab words to talk about, the universal set and the complement of a set. The universal set is just the biggest set there is that you're working with. Stop. The biggest set that you're working with. For us in algebra, usually that just means the biggest set is all real numbers. And then from there we go down to smaller and smaller sets. The rational numbers, the integers, the natural numbers, those are all subsets of the universal set, which is all real numbers. The complement of a set. Let me set the complement of a set up by saying first I have a subset. So if I have a subset of a universal set, then the complement is everything else. Every other element not in the subset. So I have a universal set. My subset is the rational numbers. The universal set was the all real numbers, the real numbers. The subset would be the rational numbers. Then the complement would be everything else that makes up the universal set, which in our case would be the irrational numbers. So what they're trying to show here is this. You have the universal set here. This whole diagram right here is a universal set. Then you have the subset A. So whatever these elements are right here, that's your subset. So then the complement of the set is everything else. This stuff right here, that's the complement. They're calling it A prime. So if I have a subset of a universal set called A in my definition, then the complement is every other element not in the subset called A prime. It's like an A with an apostrophe on it. Okay, so I find the complement of a set in chess. Anybody play chess? A few of you do. Good. Chess is a really interesting game. It's very strategic. If you know how to play chess, I'll play you sometime after school if you want, or before school. In chess, each player has a king, a queen, 2 bishops, 2 knights, 2 rooks, and 8 pawns, and each one of those pieces moves in a unique way. Let the universal set be the types of pieces that a player has. What is the universal set? Well, the universal set would be U equals, I'm going to write this in roster form, a king, queen, bishop, knight, rook, pawn. Rook, yeah, that's the one that looks like a castle. Some people call them castles. No, rook. So that's the universal set. The way that the chess pieces move is like this. A king can move in any direction as long as he only moves 1 square. So he can go diagonally if he wants, he can go horizontally, he can go vertically, but he can only go in 1 square at a time. The queen is very similar to the king. She can move in any direction she wants, just like the king, except she can go as far as she wants. She can go 1 square, she can go all the way across the board if she wants to. The bishop can only move diagonally. If your bishop is on a black square, the bishop will never leave black squares. He can only move diagonally along black squares. You also have a white bishop. The white bishop moves along the white squares only. The rook is kind of opposite of the bishop. The rook can only move horizontally or vertically, up, down, or left, right, only. Cannot move diagonally. The pawn can only move forward, 1 square. Unless it's its first move, then it can move 2, but usually it only moves 1. Okay? Now the knight can move in sort of like an L shape. It can move 2 squares and then make a 90-degree turn and move 1 square. So it winds up making like an L shape. And actually, if you look at the shape that it makes, most people don't realize this, but actually a knight starts here and can go here, 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 or here. The knight actually moves in a circular pattern. The pattern that it makes on the board forms a circle. But it moves in an L shape. You count 2 squares and then you go over 1. Okay? 2 over 1. 2 this way, over 1. 2 this way, over 1. Makes an L. So that's how all of the pieces on a chessboard move. And then you use those pieces to take your opponent's pieces and eventually try to capture his king. Let A be the set of pieces that moves from side to side. What is the complement of A? Well, what pieces move from side to side? Does the king move from side to side? He can. Does the queen move from side to side? Does the bishop? No. Does the knight? No. Does the rook? Yes. Does the pawn? No. So if the subset A is the pieces that move from left to right, from side to side, then A equals king, queen, rook. Which means A prime, the complement of the set, is bishop, knight, pawn. Another way you could show that is with the rectangle and circle. The rectangle is the universal set of chess pieces. Inside the circle would be A, and inside the circle I'm putting king, queen, and rook. Outside the circle I'm putting bishop, knight, and pawn. The universal set is all of the chess pieces. All of the chess pieces are listed here. This here is A prime, this one is A and A prime make up U. Last problem. The universal set this time is months of the year, and then our subset A is going to be months with exactly 31 days. What is the complement of that set? And we want to write that answer in roster form. So first of all, we need to figure out which months have 31 days. January does. March does. May? Do you know how to do this? Yeah, use your knuckles. The best way to do it is use your knuckles. So I'm going to try to draw a little hand here with knuckles. Okay, your thumb doesn't count. Any peak is a month with 31 days. Any valley is a month with not 31 days. And you just start with January. So here's January, 31. February, no. March, 31. April, no. May, yes. June, no. July, yes. Then start over. August, yes. September, no. October, yes. November, no. December, yes. Okay? So it's the knuckle trick. You can just kind of long on your knuckles. That's how I do it every time. I'm trying to remember if May has 30 or 31 days. I just use my knuckles. Okay, so set A is the month with exactly 31 days in roster form. That would be January, March, April, no. May, yes. June, no. July, yes. August, September, no. October, November, no. December. That's A. What's the complement of A going to be then? We'll write what? So what do I write? What do I write? A prime equals, squiggly bracket, February, the greatest month of the year. April. June. We have July and August. September. We have October, November. There it is.
Why is February the
Greatest month of the year? That's the month I was born.